I make the video. We have fun. This video is on the molar volume of a gas, which means that 1 mole of any gas has a consistent volume. What? That sounds crazy, but it's pretty much true. Alright, so Avogadro again came up with this postulate, this idea, this concept that 1 mole of any gas at the same temperature and pressure, okay? I'm going to highlight this for you so you can follow along. At the same temperature and pressure will occupy a constant and predictable volume. This is making an assumption about gases, something called the ideal gas assumption. And, that involves things we'll dig into later on. But basically, it means that all gases are going to act relatively the same. And, in fact, they are so close to acting the same that we go ahead and assume that they will basically act the same. And so, yes, like it says here, 1 mole of any gas at the same temperature and pressure will occupy a constant and predictable volume. So if we set that temperature and pressure to be these values called STP, the standard temperature and pressure, which is a temperature of 0 degrees Celsius or 273 Kelvin. If you're confused about the Kelvin scale, we'll talk more about that later. And a pressure of 101.3 kilopascals or 1 atmosphere. So those are standard temperature and pressure. If you set it at STP, then the value of 1 mole of a gas is this, 22.4 liters. So that's roughly the size of I don't know. So that's a volume of 22. It's like a box that you could hold in front of you. Okay, so 1 mole of gas, 6.02 times 10 to the 23 gas particles will occupy a volume of 22.4 liters at standard temperature and pressure. So the way you use that is you use that as one of these conversion factors. Either 1 mole is over 22.4 liters or 22.4 liters per mole. So let's practice that. All right, so here we are. Have a read through this, pause the video, and see if you can solve it. So it says a balloon is filled with 150 milliliters of a gas at STP, standard temperature and pressure. How many moles of gas is this? How many moles of gas is in the balloon? So what you want to always do in these, we're going to solve it by stacking up conversion factors. That's the preferred way. So we're going to start with the end in mind. Okay, so our target unit is moles. So we want to make sure we can get this thing into moles somehow. So we start with 150 milliliters. Okay, so that's the volume. What we need to inevitably use is the fact that there's 1 mole in every 22.4 liters. Okay, that'll help us have moles on top as a numerator, right? So that means we need to convert this 150 milliliters into liters. So we're going to need the conversion between milliliters and liters. So you could put it this way. You could say that there's 10 to the 3 milliliters in 1 liter, or sort of the standard way we tend to present that is we say 1 liter is actually 10 to the minus 3 liters in a milliliter, rather, sorry. Okay, so you do that, and that way you can stack it all up. So you do 150 times 10 to the minus 3 divided by 22.4, and if you're looking at the whole thing, all of the units will nicely cancel here and leave you with moles. And if you pump it into your calculator, which you should do, you'll get 6.70 times 10 to the minus 3. You want to make sure that this is presented in proper scientific notation, with the number out front being between 1 and 10. Okay? Okay, give this one a whirl. What volume is occupied by 27.8 milligrams of ammonia, which is NH3 gas, at standard temperature and pressure? Pause the video, see if you can sort this out. There's an extra step in this one. All right, so again, let's begin with the end in mind. Let's identify what our target unit is. We want to know what the volume is, and the standard unit of volume, as you should predict, is liters. So we want to get this thing into some amount of liters. Okay, So we start with 27.8 milligrams. What is this value? It's really important to recognize that this is a mass, okay? So somehow, we know this is all about the molar volume of a gas. We're going to have to use the 22.4 liters in a mole, okay? Which means we have to somehow get to mole, okay? So we need mole up here. How are we going to get from mass to moles? Well, you should hopefully realize that to get from mass to moles, we have to use the molar mass. So let's look up the molar mass on the periodic table of NH3. So you're going to find that nitrogen has a mass of 14, and you're going to find that hydrogen has a mass of about 1, and there's 3 of those things, NH3. So in total, this is going to be about 17 grams per mole, okay? So you can put that in there, except you got mole on top, right? Stacking up our conversion factors. So we're going to have that there's 17 grams in 1 mole, and you're going to use it like that, okay? The only other thing is, like, this is in milligrams, not grams. So we're going to have to convert that to grams first, okay? So how many grams in a milligram, okay? Or how many milligrams in a gram? And again, you could use, like, oh, there's 10 to the 3 milligrams in 1 gram, and divide. Or the standard way we've been doing it before is 10 to the minus 3 grams in 1 milligram. Okay? Now you go ahead and do the math there. You multiply 27.8 times 10 to the minus 3, divide by 17, multiply by 22.4. Check your units. They should all cancel out. Milligrams, milligrams, grams, grams, moles, moles, and leave you with the units of liter, which they do. And if you put that all into your calculator, you're going to get 0.0366 liters of NH3. Again, I didn't mention this on the last one, but you've been given 3 significant figures in the question, so you should also answer with 3 significant figures in the answer. And another one. How many atoms of hydrogen, so this one's going to test your vocabulary a little bit, are there in 19.6 kiloliters of methane gas, CH4 gas, at STP? Phew, it's at STP, because we don't know anything about other temperatures and pressures. We don't know what the molar volume is if we deviate from that. Of course, we do know it, but you'd have to look up a table of values. I'd have to give it to you, so we're basically going to stick to STP until you hear otherwise. Pause the video, see if you can figure this one out. It does have a couple of extra steps. All right, as we do, when we're trying to stack up conversion factors to solve for these, we want to begin with the end in mind. We want to begin with our target in mind. So we need to get to how many hydrogen atoms in the end. Hydrogen atoms. Okay, well, let's look at one really important thing about what an atom is. So if you have CH4, okay, you should hopefully recognize that this little unit, that thing's called a molecule, okay? And this molecule is composed of 5 different atoms. It has an atom there of carbon, okay, so it was 1 carbon atom. And then it also has 4 hydrogen atoms. So the first conversion factor that we're really going to need is we're going to need the fact that there's 4 hydrogen atoms in every 1 molecule of methane. Okay, so that's going to be a really important conversion to use, okay, to get us to hydrogen atoms. I'm going to have to make a little bit more space over here in my picture. Okay, so that'll hopefully get us to hydrogen atoms, which means we need to somehow figure out how many molecules of methane there are. Okay, we need a conversion for molecules of methane. Well, we know that there's going to be 6.02 times 10 to the 23 actual molecules in 1 mole of anything, in 1 mole of methane, okay? So, which means we have to somehow get to moles. So, how are we going to find out how many moles there are? Well, in 1 mole of methane, and this is where it comes in the fact that it's a gas at STP, we know there's going to be 22.4 liters of the thing, okay? Which means we had to have gotten to liters. And here we go. We have the thing in kiloliters, so we just have to convert to liters. So how many liters in a kiloliter? there's 10 to the 3. Kilo. It's 10 to the 3. So 10 to the 3 liters in a kiloliter. And we start off, of course, with 19.6 kiloliters. So let's make a little space and put that in there. 19.6 kiloliters. All right, so there's what we need. That's the process we have to do to get to hydrogen atoms. Have a look-see at that, and hopefully you can figure it out. If you process it all, 19.6 times 10 to the 3 divided by 22.4 times 6.02 times 10 to the 23 times 4. And again, what I would do is maybe just leave out the times 10 to the 23, and then just make your answer times 10 to the 23, and then correct it to correct scientific notation at the end. You do all that math, you're going to end up getting 2.11 times 10 to the exponent 27 atoms of hydrogen. Okay? And you should ask yourself, does this make sense? Are you expecting a humongous number like this? Yes, of course you are, because atoms are very small, and so if you have any measurable amount of them at all, you are, which you do, 19.6 kiloliters is a heck of a lot. You're expecting there to be a massive amount of hydrogen atoms, which there is in this case. Okay? So hopefully you find this helpful. Do lots of practice on this.